Hello everyone. So in this notebook, I'll be implementing a pre-trained model. So the tool I'll be using is PyTorch, and in that I'll be making use of ResNet18 model. The data set that I will be using will be from Kaggle, whether the image is of Santa Claus or not. So it will be a binary classification problem, and the link for the data set is mentioned in the first code block. So in case you want to try it out, here is the link. Second one is, since we'll be making use of ResNet18, so mean and standard deviation for ResNet18, that is for all ResNet, these models are trained on ImageNet. So mean and standard deviation for ImageNet is mentioned over here. So I will be making use of these values while creating the transformer object. So this implementation will happen in 4 steps. I have tried to make it as simple as possible, just that you should know how to code in Python. So first one is import libraries. Second one is load the data. Third one is build the model. And fourth one is train and evaluate the model. So let's begin. Libraries, import OS. In case I'll need to see what directory I'm in and where the required files are, then from time import time, this will give me time in seconds. So to calculate how much time the Epoch has taken, I'll be making use of this. Then from tqdm import tqdm, this will give a good horizontal bar for our training visualization. Then import numpy, import torch, from torch.nn, import linear. Let's just give it a minute. Okay, linear, then cross entropy loss. So linear, because I'll explain why we are going to use linear layer, because for pre-trained model, we will have to replace the last fully connected layer out. For that, I have I have imported linear, and cross entropy loss is the loss that we will be making use of in our deep learning. Then import optimizer from torch.optim import Adam. Then from torch.utils.data import data loader. Oops, data loader. Then import torchvision from torchvision.datasets import image folder, because the images that we will be feeding into our model, those are saved locally in a folder. So to read the image and to create a data set, you will be making use of image folder. Then from torchvision.models import ResNet18. So there are several models for ResNet. I'll be selecting the smallest one, ResNet18. So 18 is the number of layers. ResNet34 has more layers. ResNet50 has even more layers. So the more higher the number, the more the layers in that particular model. So this is basically the architecture, and based upon this architecture, we will be building the model. The reason I'm selecting ResNet18 is because the computation cost for ResNet18 is lowest compared to other ResNets, and my competitor system that I'm using is not that strong to train the model based upon complicated architecture. So I'll be making use of the simplest architecture, ResNet18. In case we need any other libraries, we will be importing them as and when required. Then device, since I have NVIDIA GPU, so I'll be making use of the CUDA functionality in PyTorch. So device equal to torch dot device, and I'll put in the condition CUDA if torch dot CUDA dot is available. So this particular, the thing which I have highlighted, so this will give me a binary Boolean output, whether true or false. So if it is true, it will make use of CUDA device, that is the GPU. If not, make use of CPU. Now guys, if you want to train the model, you can use both GPU and CPU, but training the model on GPU is much more faster than training it on your CPU. So let me just import it. Okay, so all these libraries are imported. One more thing that we should import is the transformer object. I just recalled from torchvision.transforms import transforms. Okay, so it should be from and not. Okay, done. Then data loader. Now create the transformer object. TFM equal to transforms dot compose. So if you want to pass in several transformation commands, then you have to pass it in list format. So first one will be transforms resize 224 by 224. So this is a standard pixel value 224 by 224 for any image that you want to pass in to the ResNet model. Then transforms dot random horizontal flip. Then transforms dot random rotation, I'll say degree as 10 degree. Then transforms dot to tensor. Then transforms dot normalize. So here you have to pass in these values normalization. First one is the mean and second one is the standard deviation. So for all the ResNet models, the values will remain the same because all these models are trained on ImageNet. It should be degrees, sorry, my bad, not degree. Done. Then let us create data sets. TrainedDS is image folder, and then pass in the path of this particular the path of the images on which you want to build the data set. So for TrainedDS, this is the path. Is in the folder is that Santa. It has a subfolder by the name of train, and in that train we have two more folders where it says whether the image is of Santa or not. So just here, yeah, so this is a folder is that Santa, in that train and test, and in train we have two folders, Santa or not a Santa, and in that we have these images of Santa Claus and not Santa Claus. Coming back to the code, so if I want to create train dataset, I'll pass in train root and transform as our transformation object. Similarly for test dataset, image folder, test root, transform as our transform object. Done. Now, if I want to see how many files we have in the train dataset and test dataset, I will just type, I will save it in this length train and length root variables. TrainedDS and len test. The reason I have saved these parameters, the length of the file, training and test dataset, that is the total number of files, is we want to calculate accuracy for every epoch. So down the line, when we will be training the model, I'll be using this len train and len test. Then index mapping. If you want to see how the image folder method has assigned the labels, for that purpose we can use TrainedDS.class2index, and it will show you how the mapping is done. So the training images are 614, test images are 616 as per this dataset, and the mapping is not a Santa is mapped 0 value and Santa is mapped 1 value. Now that this is done, then let us create data loader. Train loader equal to data loader, and we have to pass in the data set. So train data set then batch size 30, then shuffle, whether you want to shuffle the data, and say true. Similarly, test loader, data loader test dataset, then batch size 30, then shuffle equal to true. Now this batch size, you can increase the batch size provided you have a computer which can handle higher batch size. Since mine is entry level system, so if I increase the batch size, the GPU memory gets maxed out. In case you face the problem of GPU memory getting maxed out, you can reduce the batch size. But that comes with a catch. The higher the batch size, the higher the accuracy of your model. If you keep the batch size low, then model will need more number of epochs to train itself, and the accuracy will also increase very slowly. It may also happen that the accuracy will fluctuate. It will rise, decrease, if you keep batch size as very low. Now that is executed. Now let us use ResNet to build our model. So I will say model equal to ResNet18, and in this I will pass in pre-trained parameter as true. So it will make use of the ResNet18 weights and biases. And what we will be doing is just replacing the final layer, which is the fully connected layer, and we'll be replacing it. That is changing the output features from 1000 to only 2, because the case study, so in our case the output consists of only 2, whether it is Santa or not Santa. So this, whether it is Santa or not Santa. So this is the structure of ResNet18, and we'll be replacing this FC fully connected layer with our own fully connected layer. So input features will remain the same. We will just be replacing 1000 by 2. So let me just copy this. So here I can type model.fc equal to linear, and out features will consist of 2. And now if you see model FC fully connected layer output features, so instead of 1000, which was appearing before we made this change, now it is appearing as 2. And let me just move this model to GPU. So you can move the model to GPU, model or any tensor to GPU using this particular method. So to device. So why this one is safer? You can also move the tensor or model to your GPU by this method, model equal to model.CUDA. But this will only work if you have CUDA operational. That is, if your system is supporting NVIDIA GPU. PyTorch currently supports only NVIDIA GPU, which is CUDA. Recently it has started supporting Intel Iris graphics card as a GPU, but that support is available only on Linux systems and not on Windows systems. So only if your system supports NVIDIA CUDA, and you have to install that CUDA package, your CUDA toolkit. But the reason why I won't be using this in the code is, if you keep this as a uniform, it will keep this, you keep the entire code uniform. So even if you do not have GPU support on your system will be able to execute this, because if you recall at the beginning, we have written this: if your system finds CUDA as available, it will make use of CUDA, else it will make use of CPU. So even if CUDA is not available, this code will run, and the model will be run on CPU. So this is done. Then replace output of, okay, so this we have already done over here. I'll just change it over here. Now let us define optimizer. Optimizer is Adam. We'll be making use of Adam optimizer, and first parameters will be the model parameters. Second one is learning rate equal to 3e raised to -4. So 3 raised to minus 4 is nothing but 0.0003. This value is based upon the people who have made use of ADAM. The best learning rate for ADAM optimizer is 3e raised to minus 4. And weight decay that we'll be making use of is this 0.0001. Weight decay prevents overfitting of the model. So that's the reason we are making use of weight decay. Loss function, let us define loss function is cross entropy loss. Our optimizer and loss functions are defined. Now let us train the model. So for training the model, let us train the model for 3 epochs. For epoch in range 3. If you want to train the model, you can train the model for more number of epochs. But since my system is not that strong, I'll be training it for 3 epochs. When I try to run on more than 3 epochs, then it maxed out its CUDA memory, that is the GPU memory. Then let us keep training accuracy as 0. We'll be incrementing it for every batch and test accuracy equal to 0. Then since we are going to train the model, we will set train model.train. Then just type in train over here. Okay, so model.train. Then similar to model.train, down the line we will evaluate the model. So there model.eval we have to pass in. Then with TQDM, since we want a horizontal progress bar for our own understanding, with TQDM here I have to pass in data loader. Sorry, so data loader, as in since we're in the training phase, I'll be making use of the train loader. And here unit, I'll be passing it as batch because I'll be training the model in batches as the epoch. And then you have to take every iteration of your train loader. So for X train, Y train in T epoch. So first I have to set optimizer to 0 grad. So it will for every training of every batch, the optimizer will be set to 0 gradient. So that the values of previous iteration won't affect the values of the current iteration. So let me move this xtrain to our GPU. xtrain.to device. The reason is because both the parameter input and model both needs to be on the same device. So if your model is on CPU and your input parameter is on GPU, it will not work. Vice versa, if your input is on CPU and model is on GPU, it will not work. So either both the input and model needs to be on CPU, or both input and model needs to be on GPU. Now let me pass in through the model. So train probability equal to model, and here I will pass it in xtrain. And once it is trained, I will move this train probability to CPU to prevent maxing out my GPU memory. If you're already running it on CPU itself, then you don't have to do this. Now calculate the loss. Train probability. I have to pass it in loss function. First parameter will be the train probability, that is the output of the model. And second one will be the Y train here from our loader. Do not interchange the positions, because first position should always be the output of the model. If you reverse it, the Python will throw. Torch is not designed, this loss function is not designed in that way, so it will throw an error. Then after we calculated this loss, we will say torch backward. So torch backward will do the back propagation, and then we will call optimizer dot step. So it will update the model parameters. So at this phase, training ends. So now the only thing that we need is for our own understanding to calculate the accuracy. We will compare the output of the model with our Y-train, the predicted values versus the actual values. So since the model is predicting in terms of probability, we will convert the probability to the correct predictions as per in a format that is similar to Y-train. So for that, train prediction equal to torch dot max, and here I will pass this train probability comma 1 and dot indices. I'll explain you why I have done this, and I'll also explain you why I'm going to do the next step. Then train, I'll be incrementing it to train accuracy equal to 0 right now at the beginning, but I'll be incrementing it with passing through the integer as torch dot sum, and here I'll be checking how many in our batch are correct with the I'll be matching it with the actual values, predicted values versus actual values. So this will give me a boolean true false for all the 30 cases, and out of them how many are true. So for to count that, I will be making use of torch dot sum. And now to explain why I have done this, so for that I'll just create a rough couple of code blocks. So for xy, just let me just hook in my charger. So for xy in train loader, x and y, and I'll break this off. So because we only want for demonstration purpose. So x shape, it will be in terms of 30 because our batch size is 30, and this will also be in terms of 30. So if I run this, so you will see first one will be our input will be in terms of 30 images, and it will be in the format 3 because it is a color image, 3 into 224 by 224. So if I pass it through the model, so first let me just move it to our GPU, and then y prediction, I'll say y probability, not prediction yet. So I will pass this through model.x.float. So this you have to convert it to float before passing the input. And this y probability, it will be in terms of prediction. So here if you see for first example in the batch, so this is for index 0 and this is for index 1. So minus 0.4 is greater, sorry, minus this value is greater than this one. So for this, the probability of 1 is greater than probability of 0. So we should get output in this format. And if you see the actual y value from the model, sorry, from the loader, it is in this format. So we want our output in this format so that we can calculate how many predictions are correct. So for that, I'll be making use of y probability. So torch dot max, and here if I pass in as y probability, it will give output in this format. It first will be the values, that is the highest values of the 2 for all the 30 cases, and then it will give the index on which this highest value has come. So instead of this, we only want the index. So I will be making use of indices. So now it is similar to this format. And if I want to, right now it is on CUDA device, I'll transfer it to CPU. So y probe equal to y probe dot CPU, and then I'll save this in ypred. Now if you see, ypred is exactly similar to y actual, means at least the format is similar to the y actual. And now if I want to see, if I type y equal to y pred, it will show it in true false format. And if I want to count the number of true, then I will pass it in torch.sum. That's it. So tensor 9. So I'll be incrementing this to our train accuracy. So torch, so 90 will get added here to torch accuracy. So let me just remove this. This was a rough work only for our understanding. Now coming out of the loop, once all the batches are trained, I'll be calculating epoch training accuracy. So this will be the incremented training accuracy divided by total number of images in that particular loader. So since this is training, now this one is done. So coming on to the evaluation phase. So in evaluation phase, we are not going to make any changes to our gradients. So I have to write with torch dot no grad. So this will not make any changes to the gradient. Here I will look for x test, y test in test loader. I'll move this x test to our device, x test dot to device. Then test probability will be model. We'll pass x test through the model. Then I will transfer this to CPU dot CPU. Then we will calculate test accuracy. Test prediction equal to torch dot max. Here I'll pass test probability, comma 1 dot indices, and then I'll type test accuracy. I'll increment it to the test accuracy and integer torch dot sum equal to y test. Now this is done. Now for our understanding, let us print it. One more thing to calculate the time. Let me just start. In start, I will save the time at which we have started, and in end, I will save the time where we are ending the epoch. And in duration, I will calculate the difference between start and end and divide it by 60. So we get it in terms of minutes. So epoch, I will pass in epoch f string, then time taken, duration. Then coming on to next line, let us see the loss. Or we'll just type the loss in the first line itself. Okay, so here I made a mistake. It should be just loss, not the loss function itself. Loss dot get. And then on next line, we will mention train accuracy. This will be the epoch train accuracy. I think we have not calculated the epoch test accuracy. So let us do that. Epoch test accuracy is this test accuracy divided by length of our test data set. So this test accuracy. Epoch test accuracy. Now this is done. Let's hope we don't face any errors while training the model. In case we face any error, then we will debug that error. So the speed at which this gets processed also depends on the capability of your system. So if you have a good system, it will train fast. If you have not so good system, it will take time to train. At least I have GPU support, so at least it is training faster than the time it will take to train on CPU. So for first epoch, training accuracy is 89.9 and test accuracy is 93. Okay, for second epoch, it has risen to 96.9 and test accuracy has risen to 95.77. For third epoch, let us see. Okay, so for third, train accuracy has risen to 99% and test accuracy has risen to 96%. Okay, so we have trained this for 3 epochs. Now, let us see the model performance. So for sample, I already mentioned the path where these files are kept, sample 1, sample 2. So first 2 will be of center, second 2 will be of not center. Now let us check. So for example purpose, we will be making use of the pillow library from PIL import image and img equal to image. Let us read the image dot open and the path. First, I'll just show for one example and then we will be looping through the remaining. So let us display the image. Resize it to 224 by 224, so it fits over here. So I think this is Santa Claus. So yeah, so the model should predict this as Santa Claus. So let us convert it to array, pass it through NumPy img, and then img tensor will pass it through our transformer object img array. Achha, name NP is not defined. Import NumPy as MP. Image should be a PI image. Got class name. Okay, so I'm facing a bit difficulty over here. Let me just recreate an object, transformer object. Compose. Let me just copy paste this transformer object, because you have to pre-process the image before passing it through our model. So transforms dot to PIL image, sorry, PIL to tensor. This should come 100%. This should come above this, and then EFM2. Okay, I think I don't need to convert it to NumPy array. Let me just pass in the image as it is. Okay, so we did not need this because the transformer object itself takes care of converting it to NumPy array. Okay, so we got this image tensor. If you want to check the size of this image tensor, just type tensor.shape, and the input size for our model should be 4-dimensional, because we have trained our model in terms of batch size. So I'll just add one more dimension to it. img tensor equal to img tensor np dot new axis and then IMG tensor. So yeah, so that's it. So I'll just put it over here. Now, if I run this, and now if you see the shape, it is 13224 by 224. So this is the shape that we can pass to our model. Now let us pass it to our model. Let me just move our image sensor, image tensor to GPU device. And now prediction probability equal to model IMG tensor, and prediction probability, I'll just need to check the indices. Prediction equal to torch dot max dot indices, the same thing which we did in our training phase over here, to convert the probabilities to their indices. And prediction equal to PRED dot item. So this will extract the value from the tensor. So if I see, it is predicting 1. So if it is 1, then if you see the mapping, so if you see 1 means Santa and 0 means not a Santa. Let us put one condition over here. I'll save it as text equal to if Fred equal to 1, print model prediction 1, hence Santa. Else not a Santa. Model prediction. Oops. So model prediction, hence not Santa. Okay, now let us just loop it. Let me just put this demarcation. So this is the sample list. Let me just loop it over sample list for image path sample list. Let me just take this under this loop, image path. Yeah. So this is the first. So this we have Santa over here. So model is predicting as 1, hence Santa. Second one, model prediction 1, hence Santa. Third one is model prediction is 1, hence Santa. I guess he has a red color, but I don't think he's Santa. And here it is obviously not Santa, so 0, hence not a Santa. So I think our model is predicting decently. So so the video will end over here. So this video was about PyTorch pre-trained model, because we made use of ResNet18. Now I'll be making one more model where we'll be building our own model. Most of the things will remain the same, just that this part, build the model. So the only difference will be in this model. We'll be making use of our PyTorch NN module and to build our own model. So that's it for today. Stay safe. Bye bye.